add interactions or add nonlinearity terms, then refit the marginal structural model, recalculate the weights, and check the balance again. Right? Is that data mining or data fishing? Are there multiple comparison issues arising here? Usually the answer is no, because in doing all of these, we are not looking at the outcome. We are only looking at the propensity score models, and all the things that we looked at are covariates and the treatment indicator. Since no outcome is involved, of course, you still need to conditional on the facts that you estimated these models, and you need to take into account their uncertainty. But I wouldn't say there is multiple comparison issues here. Does that make sense?
Yeah. I mean, I think if you want to assume strong ignorability, then I mean everything's fine. If you're just trying to go with balance on the observables.
Okay. Okay. So now let's talk a little bit about weights. So we kind of touched upon this, where someone said, if some of the weights are large, maybe we have noisier estimates or estimators with larger variance. And we want to delve a little bit deeper into that and see why that is the case. So let's suppose that someone has a weight of 10,000 in a data set after we did the weighting. So in this case, in the pseudo population, they essentially represent 10,000 people. So if the outcome is, suppose the outcome is binary, then whether they have the outcome equal to 1, have the event or not, could have a big impact on the parameter estimate. So why is that an issue, or why is that something worth talking about? That's because if one person's outcome data can greatly affect the parameter estimate, then the standard error will be large. In other words, we'll have a noisier estimate of the causal effects. So to explain it a little bit more, let's look at this technique called bootstrapping, as it provides intuition for understanding why weights matters. So suppose we use bootstrapping to estimate the standard error of our causal estimates from fitting marginal structural models from using IPW. One way to do bootstrapping is the following. So we randomly sample with replacement from the original sample. We do that once, then we pretend that is the data we have. We estimate parameters using IPW estimation. Then we repeat this process 1 and 2 many times. We get many different bootstrapped data sets, and we have estimators from each of these data sets. Right? Then after that, the standard deviation of the bootstrap estimates can be used as an estimate of the standard error of our IPW estimator for the original data set. So this is one version of how bootstrap works. So now let's suppose we have someone in a data set who has a very large weight in the original data. Suppose we fit propensity score model, they happen to have a very large weight. Now, for this person with a very large weight, they will be included in some bootstrap samples, but not others, because when doing bootstrapping, you are randomly sample individuals from the entire data set. Right. So because they have a very large weight, whether or not they are included in the bootstrap sample will have a large impact on the parameter estimates for that bootstrap sample. And therefore, because whether including this person or not has a big impact on the parameter estimates, then we will have a lot of variability in the estimator, which will be captured by the standard deviation of the bootstrapped estimators, or the standard error for our original estimator. So hopefully this argument gives a little bit more intuition for why large weights for an individual will lead to noisier estimator from IPW. Any questions for this part? Okay, so now let's touch upon a slightly related topic. So the relationship with the positivity assumption. So remember, positivity assumption is about that we for everyone in the data, they will have positive probability to receive treatment, but also positive probability to receive control. Now, what happens when someone has a large weight? Does that have anything to do with the positivity assumption or the violation of the positivity assumption? Let's see. So remember, for someone with who received treatment, their weight is 1 over their propensity score. So if their weight is very large, then it means that their propensity score is small or close to 0, right? So this is what this first sentence is saying. An extremely large weight means that the probability of, suppose we're looking at someone with treatment 1, then for that, the probability for that person to receive treatment is very small. Now, a similar argument applies for someone who actually received treatment equal to 0. Here's a typo. This should be A equal to 0. So for someone who received treatment A equal to 0, their weight would be 1 over 1 minus the propensity score. So if their weight is large, 1 minus propensity score would be very close to 0, meaning that the probability of them receiving the control treatment is very small. So and therefore, the large weights indicate near violations of the positivity assumption. We have these very small probabilities to receive a particular treatment. Okay, so what are the practical implications? The practical implication is that large weights are alarming when fitting these models. So we always want to check if there are very large weights when actually doing data analysis using IPW. And so 2 reasons. One reason is that they lead to noisy estimates, very large variance. So that's not good. The other reason is that they may indicate a near violation of positivity assumption, and the validity of our method relies on positivity assumption to hold. Okay, so now some very basic ways to check weights include you can plot the weights. For example, the left-hand side is a histogram of the weights in a data example that we'll see shortly in this class. So here we see that most of the weights are below 5, but we may have some larger weights here and there. And this is another way to plot the weights. Instead of plotting a histogram, I am sorting the weights from all about 6,000 individuals, and I'm plotting the weights from the smallest to the largest. So we see that most of the weights are probably below 5, and we have some people with slightly larger weights. And this is another way to look at the weights. For example, you can print out some summary statistics. You can print out the mean, the median, the quantiles, etc., or the largest numbers or the smallest numbers. These are a few ways to look at weights. Okay, so suppose we identify very large weights. What do we do? And by the way, some of you might be thinking, so what is a large weight? How large is large? I don't have a definitive answer here, but something on the scale of maybe 20 to 50 would be considered a large weight in my experience. And I think it would also depend on the size of the data set and the actual applied problem that you're working on. Okay, so suppose we have very large weights. What do we do? A good first step is to look into why the weights are large for these individuals. So we would want to identify subjects who have large weights and look at what is unusual about them in terms of covariate values. How does their covariate value compare to the range of covariate values you have for the entire population? Or maybe sometimes there's a problem with their data, some typo when inputting the data, some of the values that are unrealistic. For example, if you have heart rate to be 500 per minute, that would be a unrealistic data input. And also there could be problems with the propensity score model. So that in that case, you would want to use your knowledge about logistic regression and model diagnostics to look at the propensity score model fit and try to identify issues. Or maybe there aren't issues. These are actually positivity violations. In which case we'll see how we deal with that. Although in general, it's hard to deal with. So there is no perfect solution when you have near positive violation of positivity. Okay, but either way, here we'll introduce a couple ways to handle large weights. So the first approach is called trimming the tails for the weights. So we know that large weights occur at the observations in the tail of the propensity score distribution, either when they're close to 0 or when the propensity score is close to 1. So trimming the tails can eliminate some of these extreme weights. By trimming, I mean removing subjects who have extreme values of the propensity score. So, for example, we can remove treated subjects whose propensity score are above 98th percentile from the distribution among control subjects. So for someone who has propensity score that is very small, but received treatment, we can remove that subject. And similarly, we can remove control subjects whose propensity scores are below for example, the 2nd percentile from the distribution among treated subjects. So essentially, we're removing those who have, in this case, who have weights. I can't. It's impossible to translate these two into absolute scale of the weights because they depend on the actual data. But we're removing the two tails from the propensity score distribution for those who actually fall into these tails. One important note is that if we remove some subjects by trimming the tails of the propensity score distribution, we'll change the population. So that would change the interpretation of our causal effect. We'll no longer be estimating the average causal effect on the entire population, but the average treatment effect among those whose propensity score are within certain range. So that's something to keep in mind. And we'll shortly discuss a little bit more on along that line.
I have a question.
Yes.
So, let's say I were to do the trimming method and then we kind of went back to the, what I was asking about in the beginning, where, we're adding and removing predictors, we're adding, maybe quadratic terms and, interaction terms. How do you, in your opinion, interpret who you've left out?
Good question. It's very difficult. And usually I haven't seen, I have seen many critics or criticism for doing this. And the rationale is, you're changing population. It's hard to interpret. But I haven't seen a very satisfactory argument for these type of approaches in principle. So in other words, I don't have a good interpretation for who are removed, but this is a approach that people use in practice. So if you end up using them, you need to be aware of the limitations.
Okay, thanks.
This is a politically correct answer, but that's not very satisfying, I realize. Okay. But in any case, I guess practical problems is hard. It's usually harder than doing the math and showing unbiased estimating equations. Okay, so another approach, slightly different, but very similar to trimming the weights, is by this technique called weight truncation. So instead of removing these subjects with extreme weights, we can truncate their weights by a certain threshold. So truncating means that instead of removing them, effectively setting their weights to 0, we set their weights to some threshold, say 20 or 10, like for anyone that has weight larger than that threshold. So this is the steps. This is very simple. So we can determine a maximum allowable weight, for example, 100, or we can determine a maximum allowable weight based on a percentile among all the weights in this data. So for example, the 99th percentile. So then if a weight is greater than the maximum allowable, we will set it to the max weight value. So this is very straightforward. And this is you can see this is very similar to the previous approach, except that instead of setting weights to 0, we're setting it to some max value. And again, we face this issue of changing the interpretation of the estimate. So although here we're not removing individuals, but we're manually changing the weight for some individuals. So if our original estimated propensity score were correct, then by changing the weights, the estimator is changed, it's converging to something else. We no longer have this unconfoundedness in our pseudo population. So the estimator convergers would converge to something else. So an important point throughout statistics and definitely in here in terms of changing the weights is the consideration of bias variance trade-off. So both trimming and truncation involves a bias variance trade-off. If we trim the weights or truncate the weights, we would be, you might say, we're changing the population, or another way to interpret the consequence is that we incur larger bias in our estimate when targeting the causal parameter in the original population. So we have larger bias in this case, but we would have smaller variance because the large weights are taken care of. If we do not do this kind of truncation or trimming, then if models are correct, we'll have smaller variance, smaller bias, but we would have a larger variance compared to when we do truncation and trimming. So, so here I just wanted to ask a general statistical question, not in particular related to causal inference. So what are some of the other bias variance trade-offs that you have seen, either in class or in research, that you would like to share? Oop, where are we? Okay. Anyone?
I'll just say in machine learning, there's a bias variance trade-off. So, like in terms of overfitting or more complex models that could play into consideration here. When you consider, you have to define the propensity score model with the right covariates. I mean, it is a prediction problem at its end. We don't really care what the effects are.
I see.
Just that we get them correct.
That's a good point. So can you be more specific? You know, by doing what you're incurring larger bias with smaller variance.
Yeah, so
And
if we talk about kind of like the generalizability of the model, which is the variance versus the bias, which is kind of like the MSE, or sorry, not the MSE, the actual prediction error. I guess you could say it's MSE or something of that sort. If I just pack it with a bunch of variables like what my dog ate yesterday and what the weather was, so on and so forth, then those variables are not useful. And so out of sample, it's not going to be a generalizable model. So you end up overfitting and actually not, and the predicted propensities are going to be, pretty far from the out of sample actual ones.
I see. So if you overfit the propensity score, do you incur a larger bias or do you incur larger variance? What would you say? Or both?
I mean, if you think about it as like a sample of your population, then I think you'd get bias on the final estimation because your propensities might not be correct for the population, let's just say.
Okay, that's an interesting point. I would argue the other way, actually, but you can see whether you agree with me. So my understanding of your proposal is that, so if we include too many variables in the propensity score model, then our estimated propensity score will be off so that we will have larger bias. Is that the argument? Am I getting your argument correct?
Yeah, I mean, it's kind of tough because it's like bias in what context. So within the problem, the actual sample itself, you're not going to have bias. You're going to have variance. Yep. But when you try to generalize it, then you ask, okay, what is really bias in the sense of trying to generalize?
I see. Okay, yeah, that's a very good point. I think you helped me to find a way to kind of bring a closure to this slide. So let's see if this makes sense. So now here we talked about bias variance trade-off. So what's the decision here? Should we choose bias? Should we choose variance? What do we do? And what Roy hinted upon is that we want to, in a sense, we are modeling a causal effect. We want to make some inference, or we want to get some conclusion about whether something works or not, an intervention works or not for maybe a larger population, the superpopulation that we're drawing data from. So we might want to care about the generalizability of our causal conclusion. So in this case, what's the sweet spot in terms of bias variance trade-off? It could be a minimizing mean squared error, or minimizing some kind of cross-validated version of maybe still mean squared error, maybe some other measures. So in other words, I guess my point is that in thinking about the bias variance trade-off, not just for trimming the weights, but in general, one usually want to think from the perspective of generalizability. Yeah, thanks. That's a point I haven't thought about, but I think that makes sense. Any other comments, questions on this? Okay, if not, let's talk briefly about this third approach to remedies for large weights. And this is a method, or I guess not a method per se, but this is something called stabilized weights. And different from the previous methods where there is a bias variance trade-off, when using stabilized weights, we are not doing this kind of trade-off. We are only lowering the variance without increasing the bias. Well, we'll see how this works. And by the way, we won't go too much into detail here about the stabilized weights, but on the next slide, I include some references if you want to read more. And we will likely have a homework question related to stabilized weights in homework number 2, with a lot more context on what's going on. So suppose we are considering this marginal structural model still, and suppose this is our weight, right? This is the weight that we have seen for many times. Now, one can use a slightly different weight called stabilized weight that looks like this. So what it is, what's the difference? The difference is that here in the numerators, instead of putting 1, we have a p tilde and 1 minus p tilde for some constant p tilde. This is called a stabilized weight, and one can prove that using this weight for any number of p tilde, this would lead to a consistent estimator for the average treatment effect. You can check the proof that I did for this weight, and you will see that all the math goes through. So therefore, the choice of the p tilde in terms of consistency doesn't matter. What matters is that different values of p tilde affects the efficiency or the variance of the estimator. And intuitively, one natural choice for the p tilde is that we want the p tilde to be equal to the denominator, or I guess be close to the denominator as much as possible. Although the denominator is a function of x, which can change, but the numerator is just a constant. So one p tilde that people use is the marginal randomization probability. So p tilde would be equal to the empirical probability of a equal to 1. So the frequency of the frequency of a equal to 1. There are some other choices. Okay, so just to also make sure you know a more generalized version, for a marginal structural model that models the y of a conditional on some effect modifier v, the stabilized weight can take a slightly more flexible form. So previously in the numerator we have p tilde and 1 minus p tilde for constant p tilde. Here, if we're modeling conditional on v, the numerator can also be more flexible in that it can depend on v. But it still cannot depend on the full x, but it can depend on v. The larger the v set, the more flexible your p tilde is. Now there's again this question: what's a more efficient choice of p tilde? There are some natural choices. You can read these chapters in the textbook, but I'm not sure if there are theoretical results regarding the the theoretically most efficient choice of p tilde. Yeah, if you're interested, feel free to look it up, and if you find some results, I'd love to hear about them. Okay, so that wraps up for this applied lecture on marginal structural models. Next, we'll go through some R programming examples. While I switch my presentation, any questions? Okay, if not, let me share screen. Okay, so this is some code that I wrote, borrowing from Dr. Jason Roy's course material, and I think these are practically very useful things. Some of the most useful things that you can get from this class are these R code. But the other thing that I want you to get is all these proofs about expectation of something equal to 0, which I like very much. Okay, so let's see. Well, what do we have here? We have a data set called right heart catheterization, and it's publicly available at this Vanderbilt Biostatistics Department website. And by the way, there are many other interesting data sets on this website, so feel free to check it out after class. So briefly, what this data set is about, it has the data from ICU patients in 5 hospitals. And the treatment, the binary treatment here is whether this procedure, right heart catheterization, is employed or not. And there are quite a few outcomes in this data, and the outcome that we care about in our example is a binary outcome. So whether the person had died or not in this data set. So there are a lot of confounders. For example, their demographics, their insurance information, the disease diagnosis, when they are treated, etc. And we have about 2,200 treated patients and 3,500 control patients. Okay, so let's see, what do we do in this example? We first install a few packages, then we read in the data. There are a few ways that you can get a sense of, get a brief idea of the data. I encourage you to do that on your own, because it prints out too many things. I'm not printing that on this PDF. And by the way, you can download this PDF file as well as the R code that generates this PDF file on Canvas site. So what do we do now? And is the font size okay, or is it too small for you to see? Okay, if some of you find it too small, shout out, let me know. We can try to make this bigger, but otherwise we'll continue. So these are the variables that we create. We generate from this data set. So, and I want you to focus on a couple of the most important ones. This one, treatment, is whether the treatment is RHC or not. There's a binary treatment indicator. Our outcome is whether the person died or not. And then there are a lot of other baseline covariates in our setting, and we are considering them as potential confounders. Now, in practice, you would probably want to consider more variables, or at least have some way of selecting what are the variables that are important in modeling the propensity score, or what are the variables that can be potential confounders. But in this case, for illustration purpose, let's say we have this set of variables that we consider. Then we generate a new data set, call it my data. So we'll work upon this my data. Okay, so the first thing we do, but also, scientific researchers also do in publishing a paper, for example, is that they create a table 1 for the data before doing any kind of weighting. So this is a command to do the table 1. It's called create table 1. It's from the package table 1, R package table 1. So we can create a table 1. We can ask R to do this. Then when we print it out, it tells us all these different variables, their mean and standard deviation on the treatment 0, their mean and standard deviation on treatment 1, and their standardized mean difference. We have seen this table in the lecture slides, so I won't go into details in here. So the next thing that we do is that we can estimate a propensity score model. So one way to do it is to do logistic regression. And this GLM command with family equal to binomial link equal to logit is doing that. So we fit a propensity score model, with the outcome variable being the treatment indicator, and the covariates or the regressors being all of these other covariates that we constructed. Okay, so after doing that, we can predict the propensity score value P of X or P of Xi for each I, right, for each participant. So we can call that PS using the predict command. Then if we summarize the propensity score, we can see the range of the estimated propensity scores. So we see that smallest is very close to 0, 0.04, whereas the largest is about 0.77. So, and also we can make a histogram of the propensity scores. And a similar idea, very few have very close to 0 propensity score. Some have close to 8 propensity scores, but a majority of them line within this range of maybe 0.2 to 0.6. So that's the predicted propensity scores. And by the way, I should note that if you're not very familiar with R, your type equals to response is very important here. Because it tells R to predict the outcomes here, the treatment probability in terms of the original outcome scale, so between 0 and 1. Otherwise, you'll get, if you don't have this type equal to response, you'll get different types of values in the predict command. Okay. And by the way, feel free to interrupt me if you have any questions. Okay, so now let's try to apply weighting to our estimator. So we're using the definition of weight, right? So if treatment equal to 1, the weight equals 1 over propensity score. Otherwise, 1 over 1 minus propensity score. And we can use this survey design function to create a weighted data frame, a weighted data set. So this is what we call a weighted data. So let's see what the weights look like. We can do the summary, and the weights look like this. The smallest is, of course, close to 1. It can never be smaller than 1 by definition. And the largest is 21. Okay, these are some other ways that we talked about in class. And we can look at histogram of the weight, or we can do this point scatter plot for the weights. We have went through all this just now, so I'm not spending more time on that. Okay, so now let's see something interesting. So let's create a table 1 for the weighted sample. So in this case, we need to use this command, survey create table 1, where in the data, we pass in the weighted data. So we are calculating the table 1 using a pseudo population. So here is the table 1 for the pseudo population. We see that we have pretty good balance, pretty small standard mean differences. Everything is smaller than 0.1. So that's good news. And just to make sure that this is doing what we want them to do, we can manually calculate the standardized mean difference. So for example, if we want to calculate the standardized mean difference for age, right, this would be a well-weighted mean, not the standardized mean difference. But if we want to calculate this 61.43, which is a weighted average of age in the treatment group, then we can calculate it like this. So it's an average weighted by this weight variable. And we see that this value is the same as that. So it means this is doing what we want it to do. Okay, and we have seen this standardized mean difference plot in class as well. So I will not go into that, but this is the code to create the plot if you need it. Okay, so next, let's see, how do we fit marginal structural models using the weights that we just calculated? Okay, one way is to still use the GLM function in R and put weight as the weights argument. So first, we'll fit a model of this type. So although the outcome is binary, we can still fit this model. But in this case, the interpretation of beta 1 would be still the average treatment effect, but some people call that causal risk difference when the outcome is binary. Okay, so after fitting this GLM, we can obtain its coefficients and getting its standard errors. So getting the standard errors, it's recommended that you get the heteroscedastic consistent sandwich estimator, which can be obtained through this form. Okay, so now we have beta 0 and beta 1 in the fitted model. So ATE is beta 1, which is the second parameter. So we define ATE, and we can also define the lower confidence interval and upper confidence interval based on normal approximation. So in this case, let's print out the confidence interval and the point estimate. So this is the result. Note that here we are not taking into account the fact propensity scores are estimated. And later on, we'll see how do we do that using a bootstrap. But here is the result if we just do a weighted GLM. Okay, and there is another way to fit GLM. A weighted GLM is through this survey GLM function. And you can look at it by yourself later on. But I guess the key message is that the results are the same in terms of the estimated treatment effect. Okay, so another thing we can do, instead of fitting a linear model, since this is a binary outcome situation, we can fit maybe a log linear model, or you can even fit a logistic regression. I'm not fitting that in here. But if we fit a log linear model to the binary outcome, what we get is this thing called causal relative risk. And this is sometimes of interest for binary outcomes. So this is what we do. Still, we use the weighted GLM, but here the link function is specified to be a log. You can enclose it in quotation marks or not. Both syntaxes are okay. So similarly, we get the coefficients. We calculate the standard error. Then we do the confidence interval. So this is the confidence interval and the point estimate for the causal relative risk. Okay, so next we can look at how to do weight truncation. Okay, so one thing to remember, we talked about two different ways to modify the weights. One is trimming the weights, and the other is truncating the weights. And here we're seeing how do we truncate the weights. So to put it in action, suppose we set the maximum allowable weight to be 10, then we will be replacing all the weights that are larger than 10 by 10. So this is what it's saying. And we call that truncate weight. Then we can fit a GLM, everything else being the same, but using truncate weight as the weights, then we can obtain the estimates for the average treatment effect. So if we compare these to the previous page, this is the causal average treatment effect without weight truncation. We see that the estimates are pretty close to each other, right? Slightly different, both the point estimate and the confidence intervals. So this is as expected because there aren't crazily large weights in this particular data set. The largest is about 20, but very few of them. So, and therefore it's kind of expected that after truncating the weights, we'll get a similar estimate. So one can also use this type of approach as a way of doing sensitivity analysis, although this won't be the sensitivity analysis method that we talked about in a few lectures, but this is a way to assess how sensitive the result is to these weights. Another way to fit the weights is by using this IPW package. So, and the advantage of that is that it provides some handy functions to analyze or to visualize the weights. So I won't go into details of these functions. You can look at them on your own time, but just to give you a sense of some of the functionalities it has, here is a density plot for these weights. And this dashed line is 1. Of course, no weight should be smaller than 1, but because this IPW plot is fitting a density approximation to the histogram, there are some approximation errors here. But in any case, this density approximation kind of gives you a good sense of where the weights are at, whether there are abnormally large weights. Okay, so and these are just fitting the fitting marginal structural model, fitting the weighted GLMs using weights estimated by IPW package. So nothing too special here. Okay, so now let's look at one other thing. If we want to do bootstrapping to get the standard errors, to get the, I guess, more appropriate standard errors, what do we do? So there are 2 ways to go about it. One way is to manually implement the bootstrap algorithm, and the other way is to use the boot package. The boot package is over here. So let's first take a quick look at how do we manually do bootstrap. Suppose I want to have 1,000 bootstrap samples, right? So for each of these 1,000 bootstrap samples, I randomly sample the row indices for the entire data set. And because bootstrap samples with replacement, I'm saying replace equal true. Okay, so now in this bootstrap sample, this boot data set is the original data set with boot indexed rows. So then we can, all the remaining is what we have seen. We can model the propensity score, we can construct the weights, we can add the weights to the data set, we can fit a weighted GLM, then the coefficients are the estimators from this bootstrapped sample. Okay, so we collect this coefficients from this iteration in this matrix. Okay, so this coefficients boot contains estimators from this 1,000 bootstrapped replications. So after that, we can construct confidence interval or calculate standard errors based on the bootstrapped estimates. So one way to do this is through normal approximation. For example, here we can calculate the mean and the standard deviation of these bootstrapped coefficients. Then we can use normal approximation to get the confidence interval as well as the point estimates. So these are the results. And in particular, the second role is the estimate and the confidence interval for the average treatment effect. Now, one thing that you may notice is that the confidence interval here is much wider than the confidence interval we obtained previously by using weighted GLM. So here the confidence interval is from -0.3 to +0.4, whereas earlier we have confidence interval from 0.02 to 0.07. So of course, it's expected that after doing bootstrap, because you take this additional uncertainty into account, your bootstrapped confidence interval will be wider. But by this big amount, I wasn't expecting that. So it could be that this is the case. This is what the variance should be. but it could also be that there's something wrong with my code and I haven't figured out. So if you have time afterwards to play around with this example, I would encourage you to look into it and see why there is such a big difference between the bootstrapped confidence intervals and the non-bootstrapped ones. Is that usual, or is that an artifact from this particular data set, or is that a bug in my code? Hopefully not the last choice, but we'll see. And if you find anything, you can email me or post it on the discussion forum. That would be, I would love that. Okay, so this is what we talked about as a normal approximation-based confidence interval. We can also do percentile-based bootstrap confidence intervals. Since the bootstrapped estimators, the empirical distribution of that approximates the distribution of the estimator from the original sample. And therefore, in order to get a 95% confidence interval, we can get the 0.025 and 0.975% quantiles and use these two numbers as the confidence interval. So this is the confidence interval constructed this way for the average treatment effect. And we see that, again, this is much wider than what we've seen in the weighted GLM case. Okay, so that's for manually implementing Bootstrap. And we can also use the boot package to do this. And this is pretty much self-explanatory, so I wouldn't want to get into details for this. I guess one thing to note is that the boots.ci function, so getting the confidence interval from a bootstrapped object, it has different types of confidence intervals that it can output. So if I say confidence interval type equal to all, then it would give all these different kinds of confidence intervals. Okay, any questions? And for homework number 2, we will have a programming exercise for doing marginal structural models. Not as long as this example I provided here, but you will be asked to do some of the similar things. If not, let's get started with what we will also be doing in the next slide. The new, actually, pretty sure we can't go through the entire thing, but let's see how far we can go. Okay. So, and by the way, I think this, before I say that, let's review what we talked about so far. So we used about 3 lectures to talk about marginal structural models. What a marginal structural model is, how the estimation of that is motivated by the IPW identification result, and how to do estimation, a weighted GLM, essentially. So today we will look at an estimation approach based on another identification result, the standardization. And we'll see how much time we have, but we also will touch on this another method called augmented IPW estimator. Now, I like to give spoilers before I go into all these. And I think this augmented IPW is the single most amazing estimator that I have learned throughout my PhD career. So although, later on you get to be exposed to more fancier methods and more complicated math, but I still remember the time when I learned about the augmented IPW, or the so-called doubly robust estimator. And that was mind-blowing. And the math is very elegant, but the statistical property is very, very powerful. So, and I hope that when we go through this lecture, you will more or less feel the same way. Okay. So first, let's see what we're going to talk about today. So we'll talk about an estimation approach called parametric G formula. And that is motivated by the standardization identification result. We'll also see what is an augmented IPW estimator. And we'll discuss what it means for the IPW estimator to be doubly robust. And of course, my favorite part is that we'll do some proof of why it is doubly robust. Okay. So recall that this is the standardization approach, a standardization result for identification. So assume SUTVA, conditional ignorability, and positivity, we have this approach, we have this result. So expected potential outcome equals iterated expectation, where in the iterated expectation, we have observed outcome under the treatment assignment corresponding to the potential outcome we care about. And we can take the difference to get the average treatment effect. So one natural question would be, can we use this to construct an estimator for the average treatment effect? So can we do that? One natural way would be to estimate all these expectations. In other words, we can put a hat onto each of these expectation operators. And how to operationalize that? Maybe let's fit a model for all these conditional expectations. So that's what we'll do. Okay, so let's operationalize the first part. So what are the models that we are going to fit on this to model this? Suppose we have a model called M1, which takes an argument x and a parameter beta 1 for this conditional expectation, right? For example, we can fit a linear regression model for this among those with a equal to 1. And suppose the estimated parameter value is beta 1. So therefore, this is how we would put a hat in this expectation. Now, the outer expectation here is over the distribution of x. It's over the distribution of this random variable. So one way to estimate that is to use sample average. The sample average is an empirical version of the population expectation. So we have this result. So we have this identification result for expected y1 approximately equal to, we replace this inner expectation by this model fit. And then we can replace this outer expectation by a sample average. So it's approximately equal to that. Any questions? Okay, if none, we can do a similar thing for the other part, right? We can use a model called M0 for the expected y under no treatment in x. And similarly, we can have this result hold. So this identification result can be approximated by the sample average of the linear model fits. And therefore, putting these two together, we have an estimator for the average treatment effect. So we'll call this ATE. And because this is motivated by standardization, I'll subscript it by STD. So this is our another estimator for average treatment effect. Okay, so this thing is called the parametric G formula. So let's look at it a little bit more closely, and we'll be able to see that the thing in the summation, the term in blue, is a parametric estimate of the conditional ATE, or the CATE, for individual I. The parametric assumptions are these M's. So then we take an average over the estimated CATE. So we are standardizing to the distribution of X in the entire sample. And therefore, hopefully you can see that why this is sort of a reasonable estimate for the average treatment effect. So now, why is it called a parametric G formula? It's called that because a version of the standardization result for time-varying treatments is called a non-parametric G formula. And this was originally proposed in the 1980s by Robbins. And therefore, this is a simpler version. This is just for point treatment, and this has some parametric assumptions. So that's why this is called a parametric G formula. And G in here stands for generalized, as opposed to traditional regression-based methods. Okay, so now let's take a look at the assumptions that one would need for this estimator to be valid. So what are the assumptions you think are needed for the average treatment effect estimator here to be a consistent estimator? Can any of you give me some suggestions?
The same ones that we needed for IPW.
The same ones we needed for IPW. So can you remind me what these are?
We're gonna need positivity for X.
Okay, oops, it seems that I'm not able to. Okay, I'm not able to annotate. Okay, positivity for X. So I'll just follow your
And
talking. Sutva.
And probably some kind of conditional variability.
Conditional.
No, I guess that's in Sutva. Sorry.
Okay.
Those are the two that I'm remembering.
Okay, so you said Sutva and conditional ignorability. Am I getting that correct?
Positivity also.
Oh, positivity. Okay, so Sutva, positivity, conditional ignorability. Any additional assumptions for IPW or for this one? For example, in IPW, we also need, remember, we also need a correct model for the propensity scores, right? Since the weights are calculated based on the estimated propensity scores. So I guess one question would be, do we need that assumption to be correct here? Do we need a correct model for propensity scores?
I think we need to correct the specification for N, for 2N, but maybe some part of the N, because some effects may be treatment-free effects, so they would be subtracted or canceled out.
Okay, so what she said is that, the M's are, suppose we're looking at linear regression models. So the M's are these linear regression models. So something that we need might be one of the following two. Either that we need both the M's, M0 and M1s, to be correct linear regression models, or maybe we need part of the M's to be correct in the sense that we're taking the difference, and all that we need is that the difference is a good approximation of the Kate. So anything that's in the baseline of the outcome is maybe not as important. Do I get your answer correct?
Yes, this is what I saw.
Okay, great. Okay, so we have heard a few proposals for assumptions that we need. We need these standard causal assumptions. We need Sutva, positivity, and conditional ignorability. We also need, or I guess we were debating whether we need a correct model for the propensity scores. That was needed in IPW. Maybe we need it here, maybe not. And also a new assumption that we need some kind of correct model specification for the M's. Okay, good. So let's see, what are the assumptions? So what I listed here is a group of sufficient conditions for the estimator to be consistent. So the causal assumptions and the correct model specification for both the M1 and M0. In other words, a correctly specified outcome regression model expected Y conditional on A and X. So two questions arise. Question number one, do we need propensity score models to be correct? If not, why not? Question number two, can we relax this assumption? As Qi suggested, can we mathematize, what's the part of the M1s and M0s that matters? Can we do something like that? Can we have a weaker assumption than this? So we'll address that one by one. The first question, do we need propensity score models to be correct? Here in the estimation procedure, as you see, we have no propensity scores involved. We're doing two regression models, which has nothing to do with treatment assignment mechanism, because here we're conditioning on A equals 1, here we're conditioning on A equals 0. And then we take a sample average. So, and therefore, in this particular case, the propensity score plays no role in our estimation. If you think about the estimation as an algorithm, the propensity score is not involved in that algorithm. And therefore, a reasonable conjecture is that we don't need the propensity score model to be correct. And one can actually prove that that is the case. Okay. So the second question is, can we relax this assumption? Now that's a very good observation, I'd say. And indeed, in many situations, we are able to relax assumptions like this. So if you still remember, in randomized experiments, in analyzing simply randomized experiments, we don't need the full regression model to be correct in order for our regression coefficient for treatment to be a consistent estimator for the ATE. So, however, for here, I don't have a very good answer of what is a weakened assumption, a weakened version of this assumption. What would that be? And the main reason is that I haven't thought about this possibility when preparing for this course. But there are, so let me first answer this briefly. Then maybe the next lecture, I'll give you a better answer. So there is this model called structural nested mean model. I'll type it in the chat. That's a little bit. In this model, people don't put parametric assumption on the entire expectation regression. Rather, people put modeling assumptions on the actual treatment effect. So you can think of that as difference between the two. They put a parametric assumption on the difference between the two, and that's all that's needed. So in general, yes, there are estimators that only need part of these regression models to be correct. But for this particular case, for the parametric G formula, it might be trickier to identify such a weakened assumption. You can also try that after this class, and we'll see if someone comes up with a weakened assumption. Okay, but anyway, today we'll proceed as if these are the assumptions needed. Okay, so now we have talked about the estimator, we have talked about the assumptions. The next step is inference. So how to calculate standard error. One way, we have seen similar ideas for IPW estimator as well. So this should be more familiar to you now. One way is to use estimating equation theory. The other is to use bootstraps. And by the way, there are assumptions under which bootstrap works. Bootstrap does not work universally. There are some smoothness assumptions in the estimand that bootstrap requires. Now, for this estimator as well as the IPW estimator, they are pretty smooth in the data. Although how to rigorously define that requires a lot more time to explain, so I won't explain in this class. But the short message is that bootstrap works for these two estimators. But for an estimator that we'll look at next, not in this class, called propensity score matching, we'll see that bootstrap does not work for that estimator. So bootstrap does not work universally, but it turns out that for the case we have considered so far, bootstrap works. Okay, so I won't go into very much detail of how to deriving the standard error formula using estimating equation theory, but I just want to hint upon the directions. So hopefully if you encounter similar problems in your research, this would be helpful. Not necessarily deriving a standard error for this particular estimator, but maybe if you encounter some new estimators that you want to derive standard errors for. Okay, so one way to derive the asymptotic distribution is by doing this. So we can suppose that, so you remember beta 1 hat is the parameter in this M1 model. Beta 0 hat is the parameter in this M0 model. So we can suppose that both of these coefficients or parameters come from estimating equations. So linear regression can be written as estimating equations, right? MLE can be written as estimating equations. You have GLM and many different approaches. All can be written into estimating equations. So when writing things generally, we can assume both of these come from estimating equations. We call this first one G1, we call the second one G0. Now, we can also let tau to denote the unknown average treatment effect. So in this case, instead of doing a two-step estimation, first estimate beta 0 hat, beta 1 hat, then estimate ATE as we seen here. This is the two-step formulation. We can equivalently write it as a one-step joint estimation. So we can have these three estimating equations together. The third one is just mathematically equivalent form of, if you put it ATE over here, you move it to the other hand, you get the ATE hat standardization version. So we can write these three as a joint estimating equation. Then we have our theorem telling us what's the asymptotic distribution of beta 1 hat, beta 0 hat, and tau hat from this estimating equation by taking the derivatives, if you still remember. Derivatives and expectations and the sandwich estimators etc. If you don't remember what they are, you can refer to earlier lecture slides. But anyway, so this would be a way to analytically derive the asymptotic distribution of tau hat. Okay, so before we conclude, I just want to touch briefly on the software implementation for the parametric G formula. We won't go through as detailed example as we did for the IPW. So these are some pointers for which you can look up. For example, here, the textbook by Hernan and Robbins, they provided a programming code as well, so you can check it out. They have programming code for parametric G formula. They used Bootstrap to obtain the standard errors, but they only used 5 Bootstrap replicates. That's too few. In practice, one usually needs many more Bootstrap replicates. Okay, so there's another R package called G4R developed by Hernan and Robin colleagues as well. But that package, I looked it up, and it's probably an overkill for our situation because they mainly focused on time-varying treatment settings. We'll look at these later in this quarter, but for now, this is too fancy a method, probably. And as always, if you find some software that you find useful that implements our methods, feel free to post it in a course website. So that's it for today. I'll hang around for 10 more minutes if anyone has questions to discuss. But other than that, oh, and homework is due, I guess, Monday, probably Monday evening. So remember to do that, and I'll see you next week.